and OTA for 3550, which is feedback control systems. So what I'm going to talk about today is going to be Laplace transforms. Have any of you guys seen the concept of Laplace transforms before? Or not?
Yeah.
Okay. So today, for the Laplace transforms, we're going to focus on three different things. The definition of it, what's the motivation of using Laplace transforms, and how can we apply it in the electrical engineering area. First, the objectives for this lectures are going to be state the formal definition of the Laplace transform, realize when can Laplace transform be used and how is it useful, and then last, apply the Laplace transforms to the field of electrical engineering. So let's start with the definition. Let's think of a function in the time domain, t. Time is just a strict real operator. But we can use the Laplace transform to map this linear or this completely real function into some other domain S, which is an operator, a complex operator, meaning it has a real and a complex part. We can define the Laplace transform of f of t as f of s. And the definition of it is just taking the integral that goes from 0 to infinity, adding this factor of e to the negative st over there, given that the operator is in the complex domain. The Laplace transform also defines that your time has to be bounded from the 0 to infinity. So this is just the formal definition of it. But then the next question is, okay, we have this transform, but what's the point? What do we use it for? Where can we just do anything with it? Let's take, for example, the function at derivative. With respect to time. So let's see if we take the Laplace transform of a derivative with respect to time, what would it be? So from the previous slide, we know the definition of the Laplace transform, so we can do it. We can do it this way. Correct? So if we follow this, we can solve this integral by using integration by parts. So if we just manipulate this function, I'm not going to waste the time doing the integral, but at some point we're going to have something like this. If we just keep working on this, we're just going to notice that the Laplace transform of a derivative with respect to time is just going to be the operator s times the Laplace transform of that function, just subtracting a particular condition when t is equals to 0. So by this, what I wanted to show you guys is just that we can get rid of all this differentiation process into just a simple multiplication operator, which is why sometimes using the Laplace transform might be a good idea. For the next example, taking the integration. So instead of having your function, instead of being the integral of some other function, by taking the Laplace transform, we can also arrive to the conclusion that similarly, an integration in the time domain just turns out to be a division by the complex operator S in the Laplace transform. The next question is, what's the good use of this in the electrical engineering field? First of all, like I showed you the examples before, we know that differentiation in the time domain just corresponds to a multiplication, and similarly, an integration just becomes a division. There are many other properties that make the Laplace transform to be appealing. For example, we can see time delay, or just delaying a time become just factoring an exponential, so as time scaling and frequency shift. So there's many other properties where we can actually implement the Laplace transform. It will make solving an equation much easier. So now back to where does this fit in the electrical engineering field.
It's 7 minutes now.
Okay.
Unless you want to finish this.
Okay. So for example, here we have just a RC circuit. What makes an RC circuit a little bit more complex than just a resistive circuit is just because the current in the capacitor has this relationship over here. It's just the capacitance times the rate of change of the voltage in that capacitor. So what I want to show you guys is just that if we want to solve this circuit and determining the voltage at the capacitor, we're going to have a differential equation. And if you guys want to solve it, this is the approach to solve the equation, but then it might be lengthy. So what can we do? We recognize that that's a differential equation and solve it using Laplace transforms. All those integrations and differentiations are just going to turn into multiplications and divisions. And as long as we know our input voltage, we can also take the transform of it and just with the initial conditions. But then again, the whole point was to have the function defined in the time domain. How can we go back after solving the equation in the so-called using the Laplace transforms? That's going to be a topic for the next lecture, and it's going to be how to use something called inverse Laplace transforms that is going to map your function in the complex operator back again into the time domain. Is there any other question? Okay, thank you for your time.